Okay, thanks a lot. You should all see my desktop now. I will present an ongoing research project, Annex 58, within the EBC program of IEA. And it's a little bit related to what Daniel Canard just showed us. So we try to come up with better materials, better buildings to go as low as we can in energy consumption of buildings. But most of the time we do that in the design phase. We label our buildings in the design phase, but unfortunately the reality and the actual use, energy use on site afterwards can be quite different from what we intended. So that is partly what this research project is about. It's entitled Reliable Building Energy Performance Characterization based on full-scale dynamic measurements. I will give a little bit of background. What we saw with the introduction of computer tools or building energy simulation models, we saw a growing tendency to use numerical simulations for the prediction, for the analysis of energy performance. And what is very strange, in the beginning this resulted in a decrease of in situ testing. We thought actually that we didn't need this in situ testing anymore. But what we see nowadays is that we have a renewed interest in situ testing. Testing of building components, whole buildings, both at site, on site, or as well as specific infrastructures built to test components or even whole buildings under realistic circumstances. Which is strange because of course the simulations are much faster and less expensive, but it seems that we still need this in situ testing. Some possible explanations for this renewed interest. First of all, what we notice that our building energy simulation models are a very handy tool to predict the energy consumption, predict the thermal performance, but they are not always as reliable. We can't incorporate, or we do not incorporate everything in it. So this on-site testing is one of the possibilities and one of the only possibilities that we have to help us to validate our BES tools. The second thing is that with full-scale testing we can investigate the actual performance in reality, which means including workmanship effects, including air looping, including wind washing, etc., etc. Most of these things we neglect in our building energy simulation models, and the impact is or can be rather high. Furthermore, this full-scale testing can be used to assess representativity of laboratory testing, which is also often quite an important discussion in building industry. And then the last possible explanation is the fact that some of the advanced components, I think about photovoltaic systems integrated in facades, in roofs, etc., are difficult to integrate in our BES models. They are not incorporated there. And we can use full-scale testing to build a kind of simplified, we call it a gray box model in the research project. We can build a kind of gray box model, a simplified model, which is able to predict the behavior of these advanced components, and that we can couple with our building energy simulation models. Some examples. This is a well-known figure. It's measurements done by Leeds Metropolitan University on these are co-heating tests done on different dwellings in the UK. And in purple, red purple, you see the design value. You look at the predicted heat loss, the overall heat loss coefficient, and in blue you see the measured values. And what we see is that we have quite a deviation. Sometimes they are close to one another. The measured one is always higher, and sometimes the discrepancy between both is very high. So it seems that there is a problem between the actual performance and the intended design performance. And here full-scale testing can help us to understand what's going wrong and to come to really energy efficient buildings. The second example, this is such an example of a new building facade. It's a photovoltaic integrated ventilated facade. Difficult to predict the actual behavior in advance. If you want to do it, it's based on buoyancy driven flow, so you should go to CFD simulations, but it takes a lot of time. So what we do here is we make a full-scale test of it. We measure the behavior of the building component, and then we model it in a simplified way with what we call a gray box model. A simple model which is able to incorporate all physical features of the building component and which we can then actually couple also to building energy simulation models. And this is the last example. I will come back to that later on. These are test houses in Fraunhofer Institute in Germany, which we are using in the research project for a test experiment on these real houses to validate our building energy simulation models. What is very important and what we really want to stress within this project also is that this full-scale testing requires quality, and quality on different levels. We look at the test infrastructure, whether it's on-site testing or a full-scale setup built especially to test. We have the experimental setup itself, the measurement equipment, the loggers, the data interval, how long do we have to measure it, all these kind of things. Then the data analysis. We get data with some noise on it, with some errors. How can we come to reliable conclusions? And then the use of the results, because we can't measure everything. So one or another way, we are often extrapolating the results of this on-site testing. And what is very important is that we need this quality on those different topics. And as soon as we fail on one of the topics, then we end up with some results where we have to say that these are inconclusive. We don't know exactly what we are doing. And the problem is that often some institutes or industrial partners are very well equipped to do the measurements, but are less well familiar with data analysis and use of the results. And by joining the effort, joining the know-how of the different partners, we can come up with the green arrow, which is essential to come up with reliable results. So that's the objective of Annex 58 of the research project: reliable building energy performance characterization based on full-scale dynamic measurements. So what we actually want to do is determine the actual energy performance of buildings, not the designed one, but what is the actual energy performance, and can we measure it, and how do we have to measure it? Characterize the dynamic behavior of buildings, try to build a kind of gray box model, a simplified model. Often it's a combination of thermal resistances and capacities, this kind of models, which are able to simulate in a very simplified way the dynamic behavior of the building. We want to come up with a very precise test that we can use to validate our current numerical BES-models. And as I said, it's important that we can guarantee the quality and that we give some guidelines, methodologies on how to do reliable measurements, reliable data analysis, and reliable use of the results. That's then the structure of the project. We have a first subtask, which is mainly an inventory of the state of the art. What is the current state of the art, or what was the current state of the art at the start of the project? Then we have a second subtask, which is dealing with testing infrastructure and the experimental setup. So there we want to come up with a kind of decision tree, how to do a good test experiment. The third subtask is then on the data analysis, and often this is quite some mathematics involved, and then the use of the results. And in subtask 4, we show the possibilities of the methodology and the guidelines for different applications. And then there's a fifth subtask, which is the network of excellence, which is responsible for the dissemination of the results, which is responsible for trying to guarantee this quality on the whole chain. I will quickly go through the different subtasks, not in detail, but some of the topics I will pick out. The first subtask, as I said, is in its final stage already. This will provide two booklets. One booklet on existing full-scale test facilities, really test facilities, and a lot of new ones are built nowadays still all over the world. Those are incorporated in this booklet with the possibilities and aim of the different test facilities. And then the second booklet, indicated at the right, is what are common data analysis methods, how do we use nowadays in situ testing to determine the U value, the G value of windows, to do an energy model characterization, as we call the energy signature of a building. Then subtask 2, there we try to develop a decision tree that can guide us when industry or some partner wants to characterize something, that he is guided in a way that he can determine what kind of experiments do I have to do, for how long, what kind of precision can I expect. It's important to notice that in this project we focus on two aspects. We focus on the one hand on the building fabric characterization, so the U value, the overall heat loss coefficient, thermal capacity of a building, solar transmittance, etc. On the other hand, we look at ones on the other side of the spectrum. We look at the building energy characterization, where we know that building systems and user behaviors is incorporated, but this is not a specific aim of the annex. It's more the energy signature that we try to deduce out of the dynamic data analysis, not, for instance, specific energy efficient of a system. Some examples, a lot of work has been done on the reliability of co-heating tests, determine the overall heat loss coefficients of buildings, and from there on we move further to what we call fast dynamic characterization. The co-heating test is still a quasi-stationary experiment, and in the end there is a dynamic excitation of the building. Can we not use this dynamic excitation to come to faster characterization of the building? Subtask 3 is then dealing with the dynamic data analysis. There we look mainly at the quality procedures for this dynamic data analysis. And we do this based on what we call common exercises. So we have, with the different participants in the project, we do common exercises dealing with different levels of buildings. So the first one, what you see, is a kind of scale model of a building. It's a box that has been built by one of the participants with unknown fabric properties for all other participants. And the aim is it's sent around to different institutes, different locations, where the box has been measured. We measure indoor temperature, we heat it up, we measure the response, etc. And this data is then provided to all participants, and they have to try to determine the characteristics of the box, such as the overall heat loss coefficient, the G value of the window, and just to check whether we are actually able to do that, and also for different climatic conditions. In the second step, we move then to real dwellings. This is the example I showed previously. It's the twin houses in Germany, where we use a full-scale experiment for validation of the BES-models, but also for the development of simplified models. And the last experiment we are looking at now is a high-rise building in Hong Kong. The round-robin experiment, few words. It has been measured in at the Belgian Building Research Institute under winter conditions, so rather cloudy, cold conditions. And afterwards, the box has been sent to Spain, where it has been measured in Simat, southern of Spain, under summer conditions. At the moment, the box is in Bilbao, northern part of Spain, where we measure it again under winter conditions in Spain now. The data is provided to all participants, and the aim is to see what are the capabilities, limitations of full-scale testing. Each of the partners has to decide how he measures the response of the box, and this data is then sent to all partners, and they have to try to characterize the box. They are not aware of the exact composition. Some of the preliminary results, you see here different teams with different techniques trying to apply them. I show it in the graph, it's easier. This is the overall heat loss coefficient determined by the partners. You don't see the goal value yet, the design value. But what you see is that, for instance, partner 8, if I look at the right of the graph, they are using different techniques ranging from co-heating test techniques towards black box models, RMAX models, to gray box modeling, and see which of the models are the most reliable and come up with the best results. So you see that there are quite some deviations. It also has to do with the type of technique, methodology that has been used, and that's the aim. See which kind of methodologies are applicable for buildings and how reliable are they. In SEB Task 4, then, we look to the application of the developed framework. The first one is the verification of our building energy simulation models. There we need full-scale tests. And then the second one, subtask 4.2, there we check whether the methodology that we develop, whether we cannot use it also on a limited amount of data. Nowadays, certainly when we go to new buildings and nearly zero energy buildings, we have home automation systems, we have smart meter readings, and this kind of data gives us, of course, a lot of information, and probably we can, out of that, deduce the energy performance, the characteristics of the buildings, and that's what we try to do there. And the third subtask is then show the possibilities of the on-site characterization of a building for optimizing smart grids. I will focus for a moment on the full-scale experiment that has been performed in Germany, IBP in Fraunhofer, nearby München. These are two test dwellings, very similar ones, which are comparable with real dwellings. They are not inhabited. But we simulate inhabitants by providing heat input at different moments. We have an experiment with, this is kind of imposed signals, so constant temperature with variable heat input at the moment, or a second stage we have a variable heat input, which is a random binary signal. So we heat it up to a certain level, on and off of the heater, and it gives a certain temperature response of the building. Then we have, in this case, a reinitialization period, and then we have a free-floating measurement where we just see how the building behaves based on the dynamic excitation from the outside climate. There's a very well precise document on the exercise, the validation exercise. So a very good description of the building, all the details, material properties, everything that we need actually to use it or to simulate it building in a building energy simulation model. And you see here some of the teams, they're already extended, there are more than those, with all kind of typical BES models that we use nowadays. And there's some of the results, preliminary results, the analysis in progress. For instance, of the measured temperature when it's fixed and the simulated temperature, and then the heating power that what has to be predicted. You don't see the measured value there. The people don't get it. The aim is to validate it. It's a blind validation. So they have to predict the heating power to keep this temperature at 30 degrees in this case. And afterwards we will compare it with inter-model comparison and the comparison with the really measured data. And then finally, subtask 5 is the network of excellence. There we want, actually what we want to do is guarantee, as I said, this quality on the whole chain. How do we guarantee for industry, for research institutes, that they can do really full-scale measurements on site in a reliable way? We work there together with DYNASTEE. DYNASTEE stands for Dynamic Analysis, Simulation and Testing applied to the energy and environmental performance of buildings. You see the link to the website. And together with DYNASTEE, we organize a lot of things to disseminate the results to try to guarantee the quality. So we have the website where we have regular information, we have regular newsletters, we have organization of workshops. A few weeks ago we had a webinar on co-heating test and the reliability of co-heating test. In beginning of April we have a workshop in Ghent in Belgium on co-heating and on site characterization of buildings. And then in autumn of this year we have a workshop in in the United States, LBNL, also on the more on the dynamic data analysis. At the same time, we organize yearly a summer school to give information on this dynamic data analysis. How can this done in a reliable way? We see there PhD students, we see researchers, we see people from industry following this summer school to get a grip on data analysis and knowing what they are doing. That's the team. We have 14 countries involved, 28 institutes involved in the Annex. It's quite a large group, and I think this large group shows actually the large international interest in full-scale testing and dynamic data analysis. I think the whole world is aware of the fact that we don't need to just design or label our buildings in the design phase, but that we actually have to come up with real energy efficient buildings. And we see there that this full-scale testing remains necessary, as I said, to verify numerical BES-models, to evaluate performance in reality, including workmanship, wind washing, air looping, to characterize advanced components which are too complicated just to model, and to develop our reliable, simple models that we can use in predictive control and smart grids based on the measured dynamic data. And to conclude, I think within this project, we try with different research institutes, with industrial partners, to join our effort to make a step forward towards real energy efficient buildings. And in the end, that's the only thing that counts, I think. Thank you very much for the attention. I will pass the floor back to the next speaker.